Okay. I'm Phúc and I'm master student at CMA. Today I will present the topic about scaling convolutional neural network models. And here I come to the first motivation of the first paper. And our objective is about the automatic neural network architecture shot. Normally, we can design the neural network architecture by hand, or we can design them automatically. However, the model designed by hand performs better than the models created by the automatic neural network architectures. As you can see on the right hand side, we have here the experiences. That's performance of the architecture. The first one is based on previous method, previous automatic method, NASNet, and the second one is the ResNet, the handcraft model, based on the idea of insertion. And as you can see, is the number of parameters in the model that's created by automatic method is bigger than the one created by hand, but the performance is still lower. So we need a better automatic neural network architecture. The second motivation in the second paper is about scaling convolutional neural network. So in order to increase the performance of the models, machine learning models, so we can increase the size. It means that we increase the number of layers in the models. However, we have problem with the limited hardware, because in some device like mobile phone, we need a limited hardware. We have a limited hardware, so we need some method to solve this problem. As you can see, the ResNet with 50 layers and ResNet with 152 layers, and we increase the layers, the number of layers, and it means that we increase the number of parameters in our network, and the accuracy, which is the performance of our network, also increase. So, however, if we so that we want to increase accuracy, but we also want to track we also want to keep in mind that we have limited hardware memory. So we need a better scaling convolutional neural network so to achieve this balance. And next I will come to the neural net architecture shot. So automatic neural architecture shot is a method so that we can look for the best performance models. And it is automatically. It is automatic. As you can see, is the flow chart of the neural architecture shot. We have the search space. There's a lot of architecture in the search space here, and you can see my mouse here. And there's a lot of architecture in the search space, so that we can use look for the model with highest performance. And we have search strategies, which is the algorithm. So that's we can use the search strategy to pick up the model, the architecture from search space, and based on performance estimation strategy to choose the one with the highest performance, highest accuracy. So I will go into detail what I mean about the search space. And here's the search space. All the architecture in the search space has the same structure like this one, the inception-like model like this one. And inside we have normal cell. And as you can see my mouse here, it has the input, and it has the skip connection from previous input. Shows what is the detail inside the normal cell. Is what we look our automatic architecture look for is the structure of this normal cell. And on the right side, here's the structure that we need to look for, and the combination connection here, and the operation with can be the average pooling or the mass pooling or separate convolution. As you can see from the input, we have the hidden state 0 and 1, and we go into the operation with the average pooling and mass pooling, and it's together from the hidden state 2. And whether we can decide hidden state 0, 1 or 2 to from another hidden state with the hidden state 3. This formation we call is the pairwise combination, and in this cell structure here we need totally 5 combinations like this one, and 2 last hidden state 6 and 5 we concatenate to from the hidden state 7. And in previous work, what I mean about the search strategy. As I mentioned about the search strategy algorithm, so that we can pick up the architecture from the search space and evaluate it and find the one with the highest performance. And previous work, we have 2 kinds of search strategy, which is the random search and reinforcement learning. So what I mean about the random search, in the random search, as you can see on the right side, on the left hand side, here is 2D, and there is a lot of point in a random point, not even like distributed into 2D space, but in the search space, they have likely to even distribute in the search space. In the random search implementation, all the architecture in the search space are designed equally and likely to be picked up by the search strategy, and it designed independently. And next I move on the reinforcement learning, which is previous work. And we have the controller, and controllers beyond INN reinforcement architecture, reinforcement network. And then from the controller, we sample from the search space and to pick, and then we train and evaluate the children network with it from the controller and until it converge. It means it reach some specific values. And all these experiences based on to get the validation accuracy, which is based on the validation dataset. And validation dataset is the feedback so that we can get back into the controller, and the controller over time will generate a better architecture. This is all two search strategy we had in previous work. So we want to better performance. So we in this paper we come up with the Asian evolution. So what I mean by the Asian evolution, the idea of Asian evolution is the genotype did and favor the young. So it means that it's removed the oldest architecture from the population. The population, I will mention it later, and it means that it kills the one what change earliness. Is the idea, and I will explain later in this flowchart. And at first, as you can see on the right side, we had I is the counter, and then we random individuals and from the population and add to the key. The reason why we do this, why we need from the population, so that all the architecture in the search space is likely equally to be picked up by the search strategy. And next, we need to sample from the population and uniform sample. The reason why we do this because the weaker architecture in the search space may be performing better than previous in later generation. That's why we need to sample with case sample from population again, and we need to calculate the physics from case sample and pass them at the parent like exploitation. And again, we do another transformation, is a mutation. We mutation the parent and add them at the children, train, evaluate from when we form the population at the beginning until we evaluate and evaluate children and train, evaluate children. It means the variant tournament selection. Now I will come into details about what is the mutation. On the right side, there is two kinds of mutation, hidden state mutation. And at first, in previous cell that I mentioned, there is about 5 pair combination, and we pick up randomly and choose this one. And each pair we have 2 operations, so we randomly choose independent uniformly pick up 2 operation, and the one with only one hidden state 3 we replace with another hidden state 4 like this one, and this is called hidden state mutation. And another hidden mutation, we have the operation mutation. Instead we do the same step from pick randomly from 5 pair combination, and when we choose one of 2 operation here, and then we replace the one with we don't replace the hidden state random connection like this one, but we replace we choose randomly operation with it can be separate convolution, average pooling or mass pooling, and then it is called the operation mutation. That's why it's called. And next I come up with a flow chart again. I add the beginning of the quiz and remove the one with the end of the quiz. As I said about the idea of Asian evolution, it means that I remove the oldest from the population and I increase the size. As you can see that until this some cycle, the number of cycle is chosen is less than the size of population, and in the end, after it's reached the limit of cycle, it returns the architecture with the highest performance. It means that the highest architecture with the best accuracy. And again, I want to show more detail about what the Asian by compare previous non-Asian evolution. In non-Asian evolution, we need to remove the worst model, the one with the lowest performance. And in Asian evolution, we have the idea that killing the oldest model, because this is because we don't want to zoom in the good model too early, because the weaker models can be performed better in the later generation. At the right side, you can see this comparison between 2 methods. We have compared this on the x-axis. We have the mean time accuracy based on the validation set, and m is the number of model. You can see p is the number of the size population, x is the number of sample. Even that the number of population size is smaller, the Asian evolution will perform better than 2 other methods, to non-Asian evolution. And next, performance strategy. Performance strategy is for us to evaluate the architecture and all the trained on children network, and we measure accuracy on validation set. It means that the unseen data that our model is different from training set. As you can see, it is the experiences for each algorithm, the Asian evolution, the reinforcement learning, and the random set. It's compare different architecture. In the early state, we have the Asian evolution performance better, and in the later stage, the performance better than 2 previous methods. It shows that ability of the Asian evolution that we can stop early. It means that we save the computation time and save a lot of power. On the right side, I have the ResNet, is the handcart model with 101 layer, and previous method NASNet, and the second one, the model created by Asian evolution. As you can see that the Asian model provided by the Asian evolution perform much better than the handcart model ResNet or previous method NASNet. Even that we have the nearly similar number of parameters. And next, from the automatic neural architecture, we have the good baseline model with the good accuracy. Again, I want to improve the accuracy, the performance of our model further. Then I need to scale the convolutional neural network. So in previous work, we have scale dimension with scaling, depth scaling, and resolution scaling independently. And here's the baseline model. You can see on the right side, very clear, and the input image resolution H and width. And in each state, we have each layer. We have in I state, we have N layer and 2 layer here. In different layer, different state, we have different color. And the channel, number of channel is the number of channels in the convolution layer in each stage. On the right side, we have the width scaling. It means that we increase the number of channels in the convolution layer in each stage. So by doing that, our model can recognize fine-grained feature. And as you can see on the right side, if we increase the width, it means that we have more accuracy. And the plot means here that how many operations needed to run our network. We increase width and we increase the plot. We have the better accuracy, but you can see with saturated, it will increase further because our network cannot recognize higher feature. And next, again, I have the baseline model as the same before, and I have depth scaling, which means that I scale the depth and increase the number of layers in our model. Thus, we increase the number of layers, and when I increase the number of layers, our network can recognize more higher level features. And as we did, we increase the depth, the number of slots increased, and the accuracy also increased. However, it's saturated. The reason why it's saturated is because we perform the gradient descent, and the early layers cannot be updated weight, so it's really hard to update the weight in the early state if we go deeper. And next, we have baseline models again, and we have resolution. Resolution of the image is the width and height of the model. So we scale the resolution is the input of the image, and then it means that we have more detail in the image. And then we also need to change the number convolution layers in the input so that we also increase the number of plot when we do increase the higher resolution. On the right side, you can see here, as we increase the resolution, the accuracy increase, as the plot increase, but also it's saturated because we need more layer or width to recognize more fine-grained feature or higher level feature. And in previous work, we had an observation that the higher accuracy we scale independently with depth and resolution, the accuracy will reduce if we scale it independently, these 3 dimensions together. And then another observation is that we need to balance all the dimensions, because higher resolution image, we need more layers to recognize more high level features and more channel to recognize more fine-grained features. That's why we need to propose compound scaling to better scaling our network. On the right side is based on the ImageNet with the top accuracy. As you can see that we increase the compound scaling perform much better on if we scale it independent those 2 methods, and the number of slots increase as the number of slots increase. And this experience is based on efficiency net P1 that we make for this experience. So what the proposed compound scaling means? Proposed compound scaling that means uniform scaling the network width, depth, and resolution. And here's the formula. As you can see, we have phi is the user-defined global compounding factor. It shows how many results we can have, and alpha, beta, gamma is that's how we can assign this result to the depth, the width, and the resolution. The plot is the number of operations we need to run, and it's to run the network. So the number of plot is proportional to the number of the gamma and beta power 2 and gamma over 2. And we increase using scaling all the dimensions together, it means that our plot of our model increased by gamma multiplied 2, beta about 2, multiply gamma about 2, altogether about 3. So we don't want it to reach higher than 2 power 3, so we have this constraint. And gamma, beta, and theta greater than 1. This is because we want to scale up. We want to higher accuracy. On the right side, you can see step by step we do this compound scaling. First, we fix t equal 1 and we do more screenshot and find the best value of this gamma, beta, and theta, and then we need to fix them at the constant and scale up with different phi. So here's the result of compound scaling result. You can see we have the baseline network with 50 layers, and then we scale independent the depth, the width, and the resolution. In the end, we use compound scaling, and as you can see that our compound scaling perform much better than the ResNet, 2.8. As we scale independently and we increase the depth with the resolution further, even that the number of slots increase, but the accuracy is saturated. So we need to compound scaling in this experience. In summary, in order to have a good performance model, we need an Asian evolution with the random tournament selection from the population until trained children, ablated children, xenotyrantes, and favor the young. It means that we remove the oldest from population and favor the young. It means that we don't, by doing this, we don't make sure that we don't zoom into good model too quickly and give a chance for the weaker architecture. It may be perform better in later generation. And in order to further improve performance, we need to propose compound scaling. For proposed compound scaling, we uniform scaling the network dimension, the width, the depth, and the resolution. So in the end, we can really good performance model with the high accuracy. And here the papers in this presentation I use. Thank you very much for your listening. And if you have a question, please let me know.
I have a couple of questions. Can you start by, please?
Sorry, can you wait a bit because I need to turn on my loudspeaker.
Can you go to slide 5, please?
Yeah, well, can you wait a bit? I need to connect to my loudspeaker because I cannot hear very. Sorry, wait a bit. Oh, okay. Okay. Which slide you mean?
5. Okay, I didn't quite understand which parameters you're adjust here and exactly how?
Yeah. All the architecture in such space has the insertion net module like this one, and it had the normal shell and with input connection. And our shell algorithm had a mission to look for the architecture of the normal shell. You can see on the right side screen is the structure of normal shell in general. There is different combination between operation and different kind of combination between the hidden state and different operation. Operation can be the average pooling or the mass pooling, and we have 5 combination in this, and the 2 last hidden state we just concatenate to from the hidden state 7.
Okay, so what is this number 0, 1, 2, 3, 4, 5, 6,
Then
7?
0 and 1 is the hidden state as notation for hidden state 0 and 1 is the input hidden state 0 and 1, and from that they go to the operation which is average pooling and mass pooling, and then is from the hidden state 2, and this called pairwise combination.
Sorry, I just don't understand. Like,
And it can be
so this.
yeah. Sorry, you go ahead.
If I may, so here, when you look at the figure, you have a normal cell
Yeah,
which can take 2 inputs.
Yeah.
One input comes from the previous cell and another input comes from the skip connection.
Okay.
So these 2 inputs are represented by 0 and 1 here on the figure on the right.
yeah,
Okay, and this normal cell actually has an inception-like architecture. So in inception-like architecture, you have these multiple hidden states where you have the possibilities of doing many different operations. So here you have operations like average pool, max pool, or what is shown as SCP over here is separable convolution, and what is shown as none over here is basically nothing. It will just pass on the hidden state as it is. So what you can do here is you have possibilities of doing all these different operations and making different combinations of these operations. So what this inception cell tries to search is all different combinations of connections that it can make and the different operations that it can use. And finally, in the box number 7, you concatenate the outputs from the boxes 5 and 6 together.
Okay, it's a little bit more clear now. So I have a question to the student. And so, is a gradient descent involved here somehow, or is it these like exhaustive search or some other operations that are on slide 6? Do you train the network in a normal way, or you don't, or how does that work?
number slide 6.
Yeah, but you understand what I asked, right? So you were explaining on slide 6. Yeah, go to slide 6.
No, I mean that you currently you are you explain about this search rate like this one. You mean to have a question on the question is about that with algorithm like gradient descent we use in this
I mean, just overall, how does the structure work? Because I have, usually what I do, I have a fixed architecture and I train the weights of that fixed architecture using gradient descent. And now I'm changing the architecture also. So I'm just asking, do you change your architecture and then you use gradient descent, or do you just change architecture and don't do any gradient descent? How do you train on data?
Yeah. In the architecture, we don't train. We in the Asian evolution, we don't like at first we like in this slide like at first like it is to pick up the random shot, and we is split up the architecture from search space with different architecture, and we need from population, and then from the children, and then we train average children here. The and until the and with the vision evaluation here, where we use the gradient descent, and this one we again is we reach in the end after end cycle is we return the one with the high architectures, and all this algorithm is create the baseline network, which is the one just is work on the baseline architecture, and it's created by this algorithm, and it means that we have gradient descent here, and this is where we use the gradient descent as your question.
Okay. Do other people have questions?
I do have in this sense, like, for how long do they train the network candidates? For how many epochs?
Yeah. The number we train evaluation until it's you mean train evaluate the children? Yeah. We train evaluate the children architects like until it's convent, and it mean that it conveys some specific values and this just by doing some experiences, and yeah.
I mean, because this seems like extremely computationally extensive to me, because I mean, you need to sample the architectures, you need to train those architectures to see which ones are the fittest,
Yeah.
and you need to sort of repeat this many times.
Yes.
So I got it correctly, right? So this is like really expensive to learn.
Yeah, actually we shut on the baseline network, so the model is very small, and then after this step we have baseline network, and in order to the real architecture we need to do some augmentation to make it bigger, to reach some like limitation hardware that we want. So this is just for to come with the baseline network, so the model is really small, not so big, so we can save a lot of computation time.
I see. Thanks.
Amal, maybe you have some questions?
Could you go to slide 17? Okay, so here you have the results from different types of scaling that you have done from the paper. So, I mean, why would you do compound scaling when already you scale using the depth and you get about nearly similar accuracy? Like you get about 78.1% accuracy in the second row. Then why would you go through the whole process of compound scaling and all that just to get like a 0.7% accuracy improvement?
This is the top accuracy. It means that if we increase the dimension, the depth, the width, resolution further, and the number of slots increased, however, the accuracy cannot increase. It's saturated that I explained in the previous work. That is scaling dimension independently. So we need to come up with the compound scaling, and as you can see, the performance better, and yeah, that's
Yes,
why
I agree that the performance is better by a small margin of 0.7%. But my question was, is that really worth the trouble of doing the whole compound scaling?
yeah, because as you can see on the right side, previous observation on this plot here is we increase, for example, if we increase the depth, it means the table, the accuracy in the table, we increase the, is that it's reached here, for example, it's reached here, it's saturated, and if we try to increase the depth further, and there's no chance for us to increase the accuracy further because it's saturated already here. That's why the author of this paper mentioned that is the top accuracy, because the highly performance they can reach when they scaling the diff. As well, the same thing for they scaling the resolution as well the width.
Okay, so the accuracies for the other three rows in your results table are all saturated.
Yeah,
Whereas for,
yeah, because
okay,
that's why.
whereas,
Yeah, yes.
okay, whereas for the compound scale, you're saying that it could go higher if you wanted to increase it.
Because
That also saturated.
mm, because when we do the compound scaling, we have the constraint of the like this constraint faster, and we have some constraint in the our so it's like we have the limitation of power. So this one this means that the one that we reached that constraint, and if we can if we want to the higher one, the higher the we want to higher accuracy, we can like we can replace our constraint with a higher one, and I think this the accuracy can be increased further, but in this experience, the authors just keep it at that level. That's I think, yeah.
Okay, and can you go to the previous slide where you have the constraints?
Yes.
Okay, so does these constraints, you mentioned in the motivation that the hardware was one of the limitations that you might have when you're trying to scale, right?
Yes.
So does these constraints include the hardware in any way? I mean, I just see two over here.
Yeah.
Apart from that, so how do you introduce the hardware limitation in this constraint?
Yeah. The feed is the user-defined global compound factors, and which it means that the gamma, beta, and theta, this one, and show how, and the feed is show how many resources available. So gamma, beta, and theta show how much resource we can assign to the depth, the width, and the resolution. And if we use scaling all the dimensions together, the number of slots will increase by gamma multiply beta power 2 multiply gamma power 2 altogether power 3. And because we have the constraint, so it cannot reach over 2 power 3. So that's why we have the constraints for like the hardware result here. Yeah, that's that they come up with the limitation of hardware with this constraint.
Okay, anybody else has some questions? I don't. Okay, if not, so I'd like to thank all the students for interesting talks and for participation in our seminar. Maybe Kamal will give some organizational points. I think there is also reports due pretty soon.
Yes, so the students have time till the 12th to submit the report. So they can, I think many of you would have got some hints of what to include in your report from the presentation. So please do include those points and submit your report in Studon by the 12th.
All right. Great. So please do that.